Hello everyone. In this video, we shall discuss the absolute value functions and how to sketch the graph of basic absolute value functions. And we will identify some of its properties like the domain and range and its intercepts. So first, what is an absolute value? The absolute value of x is defined as a piecewise defined function as follows. It's denoted by the following symbol, and this is read as the absolute value of x, and it is equal to x, which is our first subfunction, and this is only defined when x is non-negative or when x is greater than or equal to 0. Now, the absolute value of x is equal to the negative of the value of x whenever x is less than 0. So for example, if we have the absolute value of 5, so in here, x is equal to 5. So by definition, since 5 is greater than or equal to 0, we shall use this subfunction. So which means that the absolute value of 5 is positive 5. However, if we have the absolute value of negative 5 in here, x is equal to negative 5, and this is less than 0. So which means that we need to use the subfunction negative x. So therefore, the absolute value of negative 5 is equal to the negative of negative 5, which is positive 5. So this is how we will evaluate the absolute value of a real number. Now, how do we graph an absolute value function? So let's begin with the basic f of x equals the absolute value of x, which is defined in this manner. So we shall use the table of values, and we can assign values of x that are greater than or equal to 0 and values of x that are less than 0. So if x is equal to negative 2, then we have the absolute value of negative 2. So that's f of negative 2. And by definition, this is negative of negative 2, since negative 2 is less than 0. So the negative of negative 2 is positive 2. So that's why the value of y is positive 2. So plotting this on the Cartesian plane from the origin, we're going to move 2 units to the left and then 2 units upward. So we get this particular point here. And then when x is equal to negative 1, the value of y will be positive 1. So the point negative 1 comma 1 is the second point on the graph here. And then when x is equal to 0, the value of y is 0. So we have the origin as the third point. And then when x is equal to 1, the value of y will be the absolute value of 1, which is positive 1. So we have the point 1 comma 1. And then when x is equal to 2, the value of y is absolute value of 2, which is positive 2. So we have the point 2 comma 2. So connecting these red points by a V-shaped graph, then this is the graph of f of x is equal to the absolute value of x. Now let's consider some functions, some absolute value functions in which we have plus another constant or minus another constant inside the absolute value. So for instance, if we have f of x equals the absolute value of x minus 1. So here, we will use again the table of values and compare it with the graph of the absolute value of x. So the blue graph here is the graph of absolute value of x, which was considered in the previous slide. So using the table of values and x is equal to negative 2, then f of negative 2 is equal to the absolute value of negative 2 minus 1. And negative 2 minus 1 is equal to the negative 3. So the absolute value of negative 3 is defined as negative of negative 3, which is equal to positive 3. So therefore, the value of y is positive 3 when x is negative 2. So plotting this point on the Cartesian plane, then we get this particular point here. Now, when x is equal to negative 1, the value of y will be positive 2. So we get the 7 point. When x is equal to 0, the value of y is positive 1. So we get the point 0 comma 1. And then when x is equal to 1, the value of y is 0. So we get the point 1 comma 0. And then when x is equal to 2, we get y is equal to 1. So therefore, we have the point 2 comma 1. So connecting the red points by a V-shaped graph, then this is the graph of f of x is equal to the absolute value of x minus 1. So if we observe the graph of our function f of x is just a shift of the blue graph, which is the graph of the absolute value of x. And in this case, the graph shifted by 1 unit to the right side. So meaning we can say that this value here would tell us the number of units of movement, no, of shifting the graph of the absolute value of x. Now this time, let's consider f of x is equal to the absolute value of x plus 1. So again, we will compare it with the graph of the absolute value of x, and then we use table of values. So when x is equal to -2, we have f of -2, which is the absolute value of -2 plus 1. And this thing is equal to the absolute value of -1. And the absolute value of -1 is the negative of -1, which is +1. So we have y equals 1. Now, when we plot this, we have the point -2 comma 1. And then when x is equal to -1, the value of y is 0. So we have the point -1 comma 0. And then we have x equals 0, y equals 1. So we have the point 0 comma 1. And then we have x equals 1, y equals 2. So we have the point 1 comma 2. And then x equals 2 and y equals 3. So we have the point 2 comma 3. So connecting the red points again by a V-shaped graph would give us the graph of f of x is equal to the absolute value of x plus 1. So observe that this graph is obtained by shifting the graph of the absolute value of x by 1 unit to the left. Now we can actually get this from the given function. So the absolute value of x plus 1 can be written as the absolute value of x minus -1. So which means that this -1 would tell us that the shift will be 1 unit to the left side. So this negative sign here indicates that the movement must be to the left side. Now this time, let's consider the function or the absolute value function wherein we add or subtract a constant outside of the absolute value. So let's consider f of x equals the absolute value of x plus 1. So again, we will compare it with the graph of the absolute value of x. And then we shall use the table of values. So if ever we have x is equal to -2, that will be f of -2 equals the absolute value of -2 plus 1. Now we know that the absolute value of -2 is +2, and then we have plus 1. So this gives us +3. So therefore, the value of y is +3, and we have the point -2 comma 3. Now for the other x values, when x is -1, y will be +2. So we have this point. And then when x is 0, y is 1. So we have 0 comma 1. And then when x is 1, the value of y is 2. So we have the point 1 comma 2. And then when x is equal to 2, the value of y is 3. So we have the point 2 comma 3. And connecting the red points with a V-shaped graph, we obtain the graph of f of x equals the absolute value of x. And then we have a plus 1 outside of the absolute value. So observe here that the red graph is just a shift of the blue graph by 1 unit upward. So meaning if we have a plus 1 outside of the absolute value, it will just be a shift of 1 unit upward, from the graph of the absolute value of x. So in our next example, we will consider now absolute value of x minus 1. So from our observation from this line, we can safely say that a -1 outside of the absolute value would mean that there will be a 1 unit movement or 1 unit shift downwards of the graph of the absolute value of x. So using the table of values, if x is equal to -2, we have f of -2 is equal to the absolute value of -2 minus 1, which is +2 minus 1 equals +1. So therefore, y is equal to 1, and we have the point -2 comma 1. And then when x is equal to -1, the value of y is 0, so we have this point. When x is 0, the value of y is -1. When x is 1, the value of y is 0. And when x is 2, the value of y is +1. So we have this graph. The red graph is the graph of absolute value of x minus 1, which is the result of shifting the blue graph or the graph of absolute value of x by 1 unit downward. So this time, let's try to graph the absolute value function if there is a negative sign outside of the absolute value. So whenever we have f of x is equal to the negative of the absolute value of x, we will compare it with the graph of the absolute value of x by using table of values. So when x is -2, we have f of -2 equals the negative of the absolute value of -2. But we know that the absolute value of -2 is +2. However, there is a negative outside, so there should be a negative here. So the value of y is -2. So we have the point -2 comma -2. And then when x is equal to -1, the value of y is -1. When x is 0, the value of y is 0. When x is 1, the value of y is -1. And when x is equal to 2, the value of y is -2. So connecting the red points by an inverted V-shaped pattern, then that's the graph of the negative of the absolute value of x. So this means that whenever we apply a negative sign outside of the absolute value, it will just be a reflection of the graph of the absolute value of x along the x-axis. So here are some observations that we can infer from what we did from graphing the absolute value functions. So if the absolute value function has the following form, let's say f of x is equal to the absolute value of x minus h plus k, or plus a constant outside of the absolute value, then its graph is obtained by just shifting the graph of y equals the absolute value of x. So what we observe is whenever h is positive, so if this is positive here, and k is also positive, so when this is also positive, the graph of y equals absolute value of x is shifted by h units to the right and then k units upward. So if h is positive and k is negative, the graph of y equals the absolute value of x is shifted h units to the right and then k units downward. Now, if h is negative and k is positive, the graph of y equals the absolute value of x is shifted h units to the left, then k units upward. And then, if h is negative and k is negative, the graph of y equals the absolute value of x is shifted h units to the left, then k units downward. Now, if whenever we're considering the function having negative of the absolute value of x, then its graph is obtained by reflecting the graph of y equals the absolute value of x along the x-axis. And then if we're going to allow shifting, then f of x is equal to the negative of the absolute value of x minus h plus k is graphed by obtaining the shift of y equals the negative of the absolute value of x. So similar rules in the previous slide that will be applied in this case. Okay, now for the domain and range of the absolute value functions, if the absolute value function has the form f of x equals the absolute value of x minus h plus k, then its domain is the set of all real numbers, or the interval from negative infinity to positive infinity. So this can be explained by the fact that the graph of the absolute value function is a V-shaped graph that extends indefinitely to the left side and indefinitely to the right side. So which means everything on the x-axis will be covered by the graph. Now its range would depend on its lowest point or its highest point. Okay, so its range is y is greater than or equal to the value of k. So which means if we're looking for, if we're given with the absolute value of x minus h plus k, it will be y is greater than or equal to k. However, if the absolute value is function is in terms of negative of the absolute value of x minus h plus k, then its domain is still the set of all real numbers, but its range will be y is less than or equal to k. Or we write it in this interval. So going back to the graphing of the absolute value function, let's apply what we have observed from the previous examples. So this one is our function f of x equals the absolute value of x plus 2 minus 1. So we can actually write this as the absolute value of x minus the negative 2. And then there's a minus 1 outside. So in here, we can infer that h is equal to negative 2 and k is equal to negative 1. So when we graph this particular function, then we need to shift the graph of the absolute value of x by 2 units to the left. So this will be the lowest point for that. And then the green graph will be shifted 1 unit downwards. So the red graph here represents the graph of our function. Now the domain of this function is the set of all real numbers because the graph extends indefinitely to the left and to the right side, but its range will be from the lowest point. So the lowest point here is negative 1 and it extends upward. So which means that the range will be all the values of y that are greater than or equal to negative 1, or we can write that as brackets negative 1 comma positive infinity. Now for another example, if we have f of x equals the negative of the absolute value of x minus 1 plus 2. So the negative here tells us that the graph is an inverted V-shaped graph. And then we can write this, or we can conclude here that h is equal to 1 and that k is equal to positive 2. So this means that the graph of the given function here is a shift of the graph of negative absolute value of x. So we're going to shift it by 1 unit to the right. And then we're going to shift the green graph by 2 units upward. So the red graph here represents the graph of f of x equals the negative of the absolute value of x minus 1 plus 2. Okay. And then the domain of this function is the set of all real numbers because the graph extends indefinitely to the left and to the right. And then its range will be all values of y that are less than 2 because the graph extends indefinitely downwards. So it must be y is less than or equal to 2. Or in interval notation, we write it as follows. Okay, now, in order for us to get the intercepts of an absolute value function, we need to recall how to solve absolute value equations. So absolute value equations having this form, we have the absolute value of a times x plus b equals k, where k is non-negative. The solution of this equation is obtained by solving the following equation. So removing the absolute value, we get ax plus b, and then equate it to the value of k. And then we also solve the equation ax plus b, but equating it to the negative of the value of k. Now, if the equation absolute value of ax plus b equals k, where k is negative, then this particular equation has no solution because it's impossible that a positive number would be equal to a negative number. Okay, so as I've said earlier, the absolute value equation is important whenever solving for the x-intercept of the absolute value functions. Okay, so let's try to solve the intercepts of f of x equals the absolute value of x plus 2 minus 1. So this is the graph of this particular function. So for the x-intercept, we're going to equate our expression here to 0. So we get the absolute value of x plus 2 minus 1 and equate it to 0. And then we're going to transpose the negative 1 to the right side. So we get the absolute value of x plus 2 equals k. So now this equation here follows the form ax plus b equals k, where k is equal to 1. So that means this will result into x plus 2 equals 1 and x plus 2 equals negative 1. Okay, and then solving these equations, we get x equals negative 1 and x is equal to negative 3. So therefore, the x-intercepts are the points negative 1 comma 0 and negative 3 comma 0, which are located on this part of the Cartesian plane. Okay. And then for the y-intercept, of course, we're going to evaluate f of 0. So that will be the absolute value of 0 plus 2 minus 1, which is the absolute value of 2 minus 1, which is 2 minus 1 equals 1. So therefore, the y-intercept will be the point 0 comma 1. And then finally, let's have the function f of x equals the absolute value of x minus 3 plus 1. So for the x-intercept here, we will equate that to 0. But if we transpose positive 1 to the right side, this will become absolute value of x minus 3 equals negative 1. But remember, this equation has no solution because this absolute value here is positive, but this value at the right side is negative. So it's impossible that a positive number or a non-negative number is equal to a negative number. So in this case, there's no x-intercept. Okay, and then for the y-intercept, we have f of 0 is equal to the absolute value of 0 minus 3 plus 1, which gives us the value of 4. So if you're going to apply the graph of the absolute value of x, then that means we will have a 3-unit shift going to the right, a 3-unit shift going to the right, and then a 1-unit shift upward. So that's why there's no x-intercept because this graph here, does not intersect the x-axis, but it intersects the y-axis at y is equal to 4. So this ends our video for the absolute value functions, and I hope that you learned something from this video. And please do not forget to subscribe to my channel. Thank you for listening.